Good day, class. This week we're going to look at Chapter 3 in the NSCA textbook. And this one is probably going to be another review type of chapter for a lot of you. I know in exercise science, we went over this probably in more detail than you really wanted to. But bioenergetics can be a complicated topic, and I'm not sure if I mentioned this to you in the past, but things like this, a professor doesn't expect you to really fully understand it the first time that you learn about it. I didn't. It took me probably 8 to 10 times of reviewing some of this material to really get it in my head, right? So, first of all, it's okay to review stuff, okay? So if you learned this in the previous class, revisiting it is only going to solidify the information in your head and hopefully help you develop a better understanding of it, okay? Now, that being the case, we're not going to go into it with as much detail as we do in exercise science. Instead, we're going to focus more on the practical application of bioenergetics because, again, the whole goal of this class is learning how to put a training program together for an athlete and get some results. Okay, so what do we need to know about bioenergetics in order to be able to do that? Okay, well, this first slide kind of reminds us of the three basic energy systems that we have available that supply us with ATP. So just remember, we can't do anything without ATP, and our body stores a very small amount, okay? Therefore, even for me to get up out of this chair and walk around this tiny office I have, I don't store enough ATP in my body to do that. So my body's going to have to start producing or supplying more ATP, okay? Now, this chart is very handy because it shows us with activities of different durations, we're going to rely on one or more of these energy systems, okay? Now, this is a good time for me to say something that's important to remember. You're almost never going to rely on a single energy system for ATP. Instead, you're going to rely on all of them. The question is, which one is the primary supplier of ATP? It's almost like a continuum or like a dimmer switch, right? It's never the light's either on or off. It's just kind of you're moving how bright the light is, right? So if we look at this chart here again, it gives you 5 different time durations. And it tells you, notice this is a keyword, the primary energy system used for an activity that lasts in this time duration. So for an activity that lasts 0 to 6 seconds, which could be something like, a 50-yard dash, right? You can do that in around 4 to 5 seconds. The primary supplier of ATP for that activity is going to be the phosphagen system, okay? As we then transition into a slightly longer activity, 6 to 30 seconds, we're going to be using both the phosphagen and glycolysis, okay? As the duration then continues to increase into the 30-second to 2-minute range, now we're relying mostly or primarily on fast glycolysis, right? So I always like to use the example of a 400-meter run or, one lap around the track that surrounds a football field. That activity is a very high intensity activity if you're running as fast as you can, and you will be relying mostly on fast glycolysis, which means you're going to be producing lactate, which is why that activity is painful and uncomfortable, okay? As we then transition above the 2 minutes, now we start getting some contribution from our oxidative system. And in fact, anything longer than 3 minutes, you're going to primarily use your oxidative system, okay? So going back to programming, when you're sort of originally thinking about how to train an athlete, you want to ask yourself, with the sport this athlete plays, which energy system or systems is the athlete going to primarily use to play his or her sport, okay? Once you answer that question, you would then know which energy systems you should target with your training. So for example, if you have a marathon runner, somebody whose sport involves running for hours at a time, there's really no reason to spend time training the phosphagen system, right? So you can eliminate activities from your training program that would utilize this energy system, okay? Instead, you would primarily focus on activities that train here because that's going to be the most benefit for that particular athlete, okay? Let's move on. Actually, wait, I did put something in red I want you to notice. The inverse relationship, or I gave you the answer right away. The relationship that exists between intensity and duration. And the type of relationship that does exist is called an inverse relationship. So when one is high, the other is low, right? So intensity and duration have an inverse relationship. So when the duration is very short, extremely short, the intensity is extremely high. And vice versa, when the duration is long or high, the intensity is low, okay? So that's another sort of overall sort of guiding principle that should guide your creation of training programs and working with athletes, is there is an inverse relationship between the duration and the intensity of the activity. So athletes who participate in short duration activities, they would need very high intensity activities to train them to prepare for their sport. All right, let's move on. So we're just going to here quickly review the phosphagen system. So just to remind you of what the energy systems look like. So the phosphagen system does incorporate both the small amount of ATP that we do have stored, which would be the first thing that we use, okay? So if I do get up and jump out of this chair and start walking around, the activity or the act of getting up, which only takes me like 2 seconds, that could be primarily fueled by the small amount of ATP that I have stored in my body. That's going to quickly be gone. And the next thing that takes over to start giving me more ATP is the creatine, the phosphocreatine system. So, right, these two things both are included in the overall description of the phosphagen system. What this system does here is the ADP that we have as a byproduct after splitting our stored ATP sort of moves down here. This ADP that's left over can combine with phosphocreatine. Basically, the phosphate is stripped off of the phosphocreatine molecule and it's added to the ADP, giving us now 3 phosphates or adenosine triphosphate with a leftover creatine molecule. So this system here gets us to that like 15-second mark, right? So anything that's going to take me 15 seconds to do, most of that energy is going to be supplied by, this aspect of the phosphagen system, okay? And in general, we typically say anything that takes less than 30 seconds, most of the ATP comes from this area here. So just to review a little bit more, again, stored ATP, we only have about 2 to 5 seconds worth of ATP stored in our body. And the phosphagen system, though, is there to allow us to rapidly replenish the stored ATP that we have, okay? The phosphagen system is controlled by what we call the law of mass action. Sorry about that stumble. That basically we have these different products, right? And the concentration of these products drives a reaction. So to jump back here, when we split our stored ATP, we create a big concentration of ADP, okay? So once ADP starts accumulating in our cells, that then drives the action towards this equation, right? So we have this giant concentration of ADP that starts to accumulate in our cells. That then drives this reaction, okay? So, That's something that we refer to also as negative feedback, that the concentrations of certain molecules in our cells drive reactions to move one way or the other. And that's largely how our bioenergetic system works, okay? So just to kind of recap that, as soon as I start doing anything, my stored ATP is used. That results in a whole bunch of this ADP being present in our cells, okay? That then drives the joining of ADP to PC to produce more ATP, which I can then use to fuel that activity that I'm doing, okay? And that's sort of another way to state the law of mass action, which I'll just read the definition from the book. The concentrations of reactants or products, so that could be the ADP that we were talking about, in a solution or in our cells, drives the direction of said reactions. So moving on to the second system. Now we get to glycolysis, right? So each of the energy systems becomes a little bit more complicated, okay? The phosphagen system is relatively simple, right? Glycolysis becomes a little bit more complicated, but the good news is we get more ATP out of it, okay? We actually now are going to use a fuel source. In this case, we're talking about carbohydrates, okay? And there are two primary sources of carbohydrate that we can use. One of them is glycogen. Glycogen is simply stored glucose, right? So glucose molecules are bound together inside of cells, either in your muscle or in your liver, to form glycogen. So again, glycogen is just kind of like a big clump of glucose molecules stuck together. We can also then use the glucose that is in our blood for glycolytic purposes as well, okay? But again, the primary purpose of glycolysis is, again, to just provide ATP. In this case, ATP to fuel activities that fall into this time frame here, okay? So the example that I used earlier, the best example I could think of is a 400-meter run, okay? Now, let's think of another sport that might fall into that category, okay? A sport like football, the plays usually last less than 30 seconds. It's very rare you would have live game action in football going for 30 seconds. But a sport like soccer, and maybe to a lesser extent basketball, those sports might have live game action that proceeds for 30 seconds or longer. So those sports are going to rely more heavily on glycolysis than football does, okay? Football, just to jump back, would probably fall more into relying mostly on the phosphagen system. Another example, those various like swimming events would fall into the category of being primarily fueled by glycolysis as well, okay? So the end result of glycolysis is we are going to be left with some byproducts, okay? Chiefly, we have pyruvate, okay, which we'll see in a second. Pyruvate can either go into the aerobic energy system and lead to more ATP production, which is good, or if glycolysis is proceeding very rapidly, pyruvate gets converted into lactate, which from a certain perspective is bad. Now, lactate is not really bad, but when lactate accumulates rapidly in our cells, we essentially have to stop exercising, okay? Going back to that negative feedback concept I talked about earlier, when lactate concentration increases in a cell, there is a negative feedback effect sort of delineated upon the energy systems to slow them down, right? Because more and more lactate being produced would be a bad idea. So the concentration of lactate acts to slow down energy production, to prohibit production of more lactate. And that's why we can't run forever, right? If I was doing a 400, at the end of that 400, if I was running as fast as I could, and I wasn't well trained, I might start to slow down towards the end of it, and that would be evidence of lactate accumulating in our cells negative feedback then acting to slow glycolysis down, leading to less ATP production, which would then lead to me having to slow down or possibly stop altogether near the end of my 400-meter run. So again, there's two fates for pyruvate. If our exercise intensity is a little lower, the pyruvate can go into the mitochondria, and that's called aerobic glycolysis or slow glycolysis. However, if our exercise intensity is near maximal, we're going to be relying on fast glycolysis, and in that case, the aerobic energy system is not accepting pyruvate, so the pyruvate has to combine with hydrogen to form lactic acid, okay? Now, it is important to note that lactic acid is not the cause of fatigue. It just sort of promotes the sensation of fatigue based upon what I mentioned earlier. When lactate concentration rises, ATP production falls, and that then leads to the inability to sustain muscle contraction, which is the textbook definition of fatigue, okay? So it doesn't cause fatigue, but it sort of promotes what does cause fatigue, which is lack of ATP availability. So what is the energy yield of glycolysis? Now, we do get some ATP from it, but not very much. We only actually get 2 ATP per molecule of glucose or 3 per molecule of glycogen. In the grand scheme of things, that is not very much, but that also explains why we cannot sustain high-intensity activity for very long. We're accumulating lactate while not really producing that much ATP at the same time, right? So that's why we can only sustain those activities all out for 30 seconds to 2 minutes, depending upon your training level, okay? Now, what controls glycolysis? Again, thinking back to that whole idea of negative feedback, okay? It's stimulated by ADP, PI. Now, where do those come from? Well, let's jump back real quick and take a look, right? When we initially split ATP in step 1, we are producing ADP and PI, okay? And those things begin to accumulate in our cells, those products then act to start stimulating glycolysis to start doing its thing, right? There's a few other products as well that will stimulate them, but I'm not going to mention them right now, but just know that there are some other things that stimulate glycolysis. But on the other hand, it is inhibited by a few things as well, okay? It's inhibited by ATP. Well, think about that. If ATP concentrations are high in your cell, then there's no reason to produce more, right? So when I'm sitting here in this chair, theoretically, glycolysis activity is low because I'm not using ATP, and therefore ATP concentrations in my cells are high. Now, as soon as I start getting up and moving around, ATP concentrations in my cell will drop, right? And then glycolysis will be stimulated to start ramping up its activity, okay? Same idea here. If CP concentrations are high, that indicates your cell is energized, so there's no reason to produce more ATP, okay? Then we also have some enzymes here that control glycolysis. These things here would inhibit this enzyme and therefore inhibit glycolysis. This enzyme is called phosphofructokinase. We abbreviate that as PFK, and that's what we call the rate-limiting enzyme of glycolysis. So these things here stimulate it, these things here inhibit it. And that's how this cycle as a whole is either stimulated or inhibited. All right, moving on. So what happens when we rely on fast glycolysis? Remember we said when we're using fast glycolysis, lactic acid is going to be a product, okay? Eventually, if lactate does continue to accumulate, we may reach this point that we refer to as the lactate threshold. Okay, the lactate threshold represents the increasing reliance on anaerobic metabolism. Okay, so if you notice here, this line here indicates the concentration of lactate. So, and then down on this axis, the x-axis, we have exercise intensity. So at lower exercise intensities, lactate does not really increase much. Resting lactate levels are usually around 1 millimole per liter. Okay, so we can exercise at a light intensity and not see much accumulation of lactate. But as exercise intensity continues to increase, now we start to see this increasing concentration of lactic acid. Okay, it starts to go up, right? And that's because low intensity exercise, we can use our oxidative system. But moderate to high intensity exercise is going to rely more on the anaerobic energy systems or glycolysis, leading to, you got it, the production of lactate, right? So again, as exercise intensity starts to accumulate, as exercise intensity increases, lactate is going to start to accumulate, and eventually we're going to reach this point where we have this exponential increase, right? So here it's sort of a smooth, slow increase, but at this point we have this inflection point. An inflection point means where there's an obvious break or abrupt increase in the line, and you can see that point here. And this point is labeled the onset of blood lactate accumulation, or the OBLA. That's the acronym that we use to say it more quickly. That occurs at a level of 4 millimoles per liter, right? So the lactate threshold we consider to be at a level of 4 millimoles per liter. Okay, so once your blood lactate gets above this concentration, usually then fatigue is going to occur shortly thereafter, right? So practically, this is a useful thing to know. If you have an athlete, let's go back to the 400-meter runner. Okay, when a 400-meter runner is training to get better, they should train above the lactate threshold, because exposing your body to high levels of lactate will cause this whole curve to shift to the right, which means after training, they can exercise at a higher exercise intensity because less lactate accumulation will occur. Okay. On the other hand, for competition, you'd want to compete slightly below the lactate threshold because you don't want to fatigue out too early. Okay. Now maybe at the end of the event you push it above the lactate threshold, but early in the event, sorry, my southern accent came out, you would want to stay below the lactate threshold. So this is a pretty important concept for the training of certain athletes, because you can really improve performance by sort of identifying where somebody's lactate threshold is and having them train above it, right? And it's actually a pretty easy way to determine without drawing blood, which is the way we do it in the lab. You just have to sort of identify at what heart rate you lose your ability to carry on a conversation. Okay, when I'm above my lactate threshold, I'm breathing, I'm hyperventilating. Okay. Below my lactate threshold, I should not be hyperventilating, and I should be able to talk to somebody. Okay. So that's a way maybe you all can actually, if you're bored one day, go wear a heart rate monitor and sort of slowly increase your exercise intensity and determine at what heart rate you start to hyperventilate, and that will give you a good idea of the heart rate at which your lactate threshold is currently found. Okay, let's move on. Usually that occurs, we express it typically as a percentage of VO2 max. In untrained individuals, it's at a lower percent of VO2 max. With trained individuals, it's usually at a higher percentage of VO2 max. And that kind of explains what I said earlier. By training to improve your lactate threshold, you can shift it to the right and actually exercise at a higher intensity without experiencing lactate accumulation. Okay. So this question that I pose here, what happens when an athlete crosses the lactate threshold, we can kind of refer back to a few things that we mentioned earlier, right? Once they cross the lactate threshold, lactate is going to start to accumulate in the cells spill over into the blood, okay? And that's going to have a negative feedback effect on glycolysis, okay? So glycolysis is going to slow down. Now, what are the implications of that? If glycolysis slows down, suddenly we're not producing as much lactate, but we're also not producing as much what? We're not producing as much ATP, and therefore our ability to sustain that level of muscle contraction will diminish, and we will experience fatigue, right? Again, fatigue can be technically defined as the inability to sustain a given level of force production, okay? Lactate leads to reduced ATP production, which leads to the inability to sustain force production, so we are fatigued, to put it in quotes, okay? This is a question that I think is posed in one of your assignments, so when you're doing the assignment, jump back here to, I'm not sure what slide this is, but that'll give you a good description of how to answer that question. Okay, so then finally we get to the oxidative system. To be honest with you, it's not used much in most sports, okay? Most sports that you think of that are played on a field, they're going to rely mostly on the other energy systems. Now, aerobic energy production is very important for recovery, okay? So there is an advantage to being aerobically fit because you'll recover faster, right? So, and honestly, if you think about the sport of soccer, the field is so big, a lot of times the players are running at a lower intensity with short bursts of high intensity activity. So during that lower intensity movement that the soccer players would be performing, they're going to be relying on the aerobic energy system. And as I mentioned, when we're recovering from those high burst activities, we're using aerobic energy production. When a basketball player, when there's a break in the action, there's a foul, the ball goes out of bounds, whatever happens, and they stop moving or they kind of start moving, they go from sprinting to walking, the aerobic energy system is going to kick in and start helping us recover for the next burst of activity, okay? However, if we have to give an example of an activity that is primarily fueled by the aerobic energy system, I think that we could look at any distance events. So long distance swimming, long distance running, and long distance doesn't mean a marathon necessarily. I mean, even like a 5K, 5,000 meter run, which is about 3.1 miles. That's going to take, even the fastest athlete, that's going to take them 15 minutes. So that's still going to be primarily fueled by the oxidative system, okay? The benefit of this system is it can not only use carbohydrates, but it can use fat for fuel as well. Fat is going to give us a ton more ATP. Remember we said that from glycolysis, we only get 2 or 3 ATP per molecule. With the oxidative system, we can get hundreds of ATP per fatty acid, which is a big benefit of it. And that's why you can sustain the activity for so much longer, because you get so much more ATP per molecule of substrate, which substrate just refers to a molecule that is used to facilitate energy production. Now, two, carbohydrate and fat. So carbohydrate represented here. Remember, from glycolysis, we're left with pyruvic acid. Fatty acids are over here, and even amino acids can be used as well, although they're very rarely used for energy production. But all three of them can enter into the aerobic energy system because they all three get converted into what we call the common entry molecule, which is acetyl-CoA. Okay, fatty acids, carbohydrate-based pyruvic acid, or amino acids. All three of them get converted into acetyl-CoA, and then that molecule enters into the Krebs cycle, which is the first stage of aerobic energy production. We're not going to review this. I just wanted to kind of point this out to you all. This is what the first stage of aerobic energy production is, the Krebs cycle. And this, again, I said as our energy systems go from 1, 2 to 3, they get more complicated. This is a complicated cycle. And essentially what we're doing with the Krebs cycle is we're stripping out hydrogens from the acetyl-CoA molecule. Hydrogen is really where, in the electron that is bound to hydrogen, that is really where the energy lies, okay? So what we're doing in the Krebs cycle is we're harvesting these electrons from the molecule, and then we're going to send those electrons to phase 2 of the aerobic cycle, which is not pictured, but it's called the electron transport chain, okay? So again, we don't really need to get into that in detail now, but let's talk about some things that we do want to know. Let's again talk about what stimulates and inhibits this system. And they're going to look much the same as what we saw with glycolysis. The rate-limiting enzyme for the Krebs cycle is isocitrate dehydrogenase. And that is stimulated by the same thing that stimulates the other systems, ADP. And inhibited by the same thing that inhibits the other systems, and that's ATP, right? So let's think about that again for a second. I said earlier, when your ATP levels are high, it's kind of like your battery is fully charged, right? Your battery on your phone is at 100%. When your battery on your phone is at 100%, there's no reason to charge it, okay? That's kind of the message that high ATP gives to your cells. On the other hand, ADP, being in high concentration, is kind of like when your battery on your phone is at 10%, right? It's red, so you need to charge it, or you need to start producing more energy, right? So high ADP concentrations is a sign or sort of a symptom of your cellular energy levels being low. High ATP concentrations is a sign of your energy levels being high, right? And when your energy levels are high, there's no reason to make more, so your energy systems are inhibited. When your energy levels are low, you do need to make more, so that then stimulates your energy systems to ramp up their activity to make ATP. So both the Krebs cycle and the electron transport chain are stimulated and inhibited by the same things. Okay, so we already saw this chart, but it's a good one to revisit. And sort of the contrast with this chart here that shows the capacity and the speed with which these systems produce ATP, and they're also inversely related, much the way that we said this chart is inversely related, okay? So this is a ranking. So in terms of the rate or the speed of production, the phosphagen system is the fastest, but it produces the lowest amount. So inverse relationship. On the other hand, on the opposite extreme, the rate of production is the slowest with oxidation or the aerobic system. However, we get the most out of it, or we have the highest capacity for the amount of production, right? In the middle, we have slow glycolysis. Is kind of like the rate is okay, the capacity is okay, right? But again, it's an inverse relationship, sort of like we showed over here. But the reason why we can sustain activity for so long here at a low intensity is because we produce such a high amount of ATP with the aerobic energy system. So here we're looking at the continuum. Remember I said that we're never relying completely on a single system, but there's a percent contribution from each. What this chart here is showing us is if somebody is doing an all-out bike test that lasts 200 seconds, okay? As we move from early to late in the activity, notice that the percent contribution is going to change throughout the course of this activity. So in the first 5 seconds of the activity, 100% intensity, 96% of that ATP that we're using comes from anaerobic production, only 4% comes from aerobic. As the activity proceeds in duration, exercise intensity is going to drop because our anaerobic capacity to produce ATP is going to fall. At the same time, our aerobic contribution is going to increase. But as we saw on this page, if we jump back real quick, intensity of events that rely on the oxidative system are low, which is why we see the intensity up here start to drop, okay? So again, we kind of see that inverse relationship. When one system is high, the other is low, and as the duration of the activity proceeds, anaerobic contribution drops while aerobic contribution increases, and the consequence of that is our intensity is going to drop, okay? This chart down here gives us an idea of how long it takes to recover from different activities, okay? And this is very much related to intensity as well. The higher the intensity of the activity, the longer the recovery period needs to be before somebody can perform the activity again at a high intensity, right? So if we're relying on the phosphagen system, 90 to 100% of our maximum power, our time that we can maintain that intensity is low, and it's going to take us longer to recover. So look at it like this way. If our work period is 10 seconds, then our rest period needs to be 120 seconds. So that's what the 1 to 12 ratio looks like, okay? Or if our work period is 5 seconds, we would multiply that by 12 to know that our rest period needs to be 12 times 5 is 60 seconds, right? So we would look at that as like 5 seconds on, 60 seconds off, or 10 seconds on, 120 seconds off, right? So this could guide recovery. So if you're designing a training program for an athlete and you know that that athlete primarily utilizes their phosphagen system for their sport, your interval training work to rest ratios should look like this. Now, if you're doing an athlete that relies on the oxidative system, it's more of a 1-to-1 work to rest ratio. But if you're doing a 3-minute activity, that's your work, then the recovery would also be 3 minutes as well, okay? Or 1 to 3. So the ratios here are not super different. This is the one that's the biggest, that's the most different from the others. You know, as we get into program design, we'll kind of revisit this topic in later chapters. This is more of just an introduction to the idea of exercise duration and recovery as it relates to the energy systems, which is why we're talking about it right now. Okay, so as far as recovery, let's kind of stay on this topic for a minute. We see that as we saw over here, our phosphagen system is depleted very rapidly. And it shows on this slide that 50 to 70% of our muscle phosphagens, creatine phosphate specifically, is depleted in 5 to 30 seconds, okay? However, it can recover pretty rapidly, okay? And what this is telling us is that most of your ATP that you burn, or use, I should say, during a 5 to 37-second all-out activity is recovered or replenished in 3 to 5 minutes, with complete recovery in only 8 minutes, okay? Now, again, this is on a very short duration, high intensity activity. So keep that in mind, okay? What that tells us, though, is our body is very good at restoring cellular energy levels. Now, the more they're depleted, the longer it's going to take, and the more lactate that is present, the longer it's going to take. But for an activity that is very short, like this, there's not going to be any lactate production. So the recovery is going to be very rapid, and as we see here, it can be as rapid as full recovery in only 8 minutes of activity, or inactivity, I should say. Now, when we do tap into glycolysis, resulting in lactate production, it's going to take a little bit longer to replenish what we depleted during this activity, because we're talking about a longer duration activity. greater depletion of resources and higher accumulation of byproducts. And again, I'm talking about lactic acid in that instance. Now, ATP and creatine phosphate are replenished sort of intrinsically. In order to replenish glucose and glycogen, we're going to have to take in fuel, okay? And of course, but when I say that, I'm talking about we have to consume some carbohydrate, okay? So it's recommended in a post-workout window that you do ingest some carbohydrates in order to facilitate more rapid recovery, okay? The guide from the NSCA is 0.7 to 3 grams of carbohydrate per kilogram of your body weight, okay? Just to remind you, you calculate your body weight in kilograms by taking your body weight in pounds and dividing it by 2.2. That gives you your weight in kilograms, and then you could then apply these numbers to your weight in kilograms to figure out how much carbohydrate you should take in a post-workout window. And it's usually recommended to do that within 2 hours, and I've even heard up to 4 hours. I guess it depends on how fast you want to recover. If you consume the carbohydrate more immediately after your workout, you're going to recover a little bit faster, okay? But this is going to take a little bit longer compared to what we saw with the phosphagen system. What we're looking at here is the primary limiting factor for different activities of different duration. So again, we're looking at a ranking. And notice it's telling you the most probable, like we don't know exactly, but this is the most likely culprit. So if we look at this different activities, so if we look, for example, at the 400-meter run, what this is telling us is the least probable limiting factor is our stored carbohydrate or fat, because the event doesn't last long enough for us to deplete our fuel sources. Therefore, the reduced pH resulting from the lactic acid production is going to be the limiting factor. Okay. Now, on the other hand, longer duration events such as a marathon or a triathlon, stored carbohydrate is more likely to be the limiting factor there, because we're going to basically deplete our body of carbohydrates. So that's going to take some time to do, right? You're talking about a couple hours of exercise. You're not going to deplete yourself of glycogen in these shorter duration events, okay? So, that's another thing to consider for athletes, right? If an athlete is performing in a high intensity activity that lasts a couple hours, which you could even look at like a basketball game, right? The players who are on the floor most of the time, they're going to see some pretty significant glycogen depletion because they're exercising hard for about 2 hours. So they're going to want to place a priority on replenishing glycogen in the post-workout window. Now, something like this, a very short duration activity, the limiting factor is going to be the phosphagen system. And as we saw, that gets replenished very rapidly, okay? So an athlete who does the 100 is going to recover much faster than an athlete who does the 400 or the 5,000 meter, right? Because of the energy system they're primarily relying upon and how fast the resources that fuel that energy system get replenished. Okay, let's see where we are here. We're going to finish up here with recovery. So the duration and the intensity of your activity is going to influence, as we just talked about, how long it takes to recover. Okay, and what you'll see is during that recovery window, your oxygen consumption levels are going to be elevated, and that is shown by the fact that your breathing is elevated. If your breathing is elevated, then your oxygen consumption levels are elevated. And the reason why it stays elevated post-workout for a period of time is because your body is bringing in oxygen to help replenish ATP, creatine phosphate, and also to help us get rid of the lactate, right? Lactate can enter into the aerobic energy system where it has to combine with oxygen ultimately to produce ATP, okay? So what we're kind of looking at here is a lower intensity activity where we do not accumulate much oxygen deficit because we reach a steady state very rapidly. The recovery rate is a little bit faster, okay? EPOC, excess post-exercise oxygen consumption, is shorter, so we recover faster. So think about this as going for a walk around your neighborhood or the campus. You might have a slight breathing elevation once you finish the activity, but it'll drop off pretty quick. On the other hand, if you go out and sprint around the campus or sprint around the block, high intensity for 1 minute, you're going to have a similar rate of reduction of oxygen consumption, but it's going to not return to resting right away. Here, it touches the blue, indicating you're back to resting. Here, it does not touch because you're not fully back to resting. And in fact, your oxygen consumption might stay slightly elevated for 24 to 48 hours post-workout, okay? And that just shows that because of this high intensity activity that you did, you disrupted homeostasis a lot. So it's just going to take a longer period of time to restore homeostasis, and your body's going to bring in elevated levels of oxygen to help you manage that restoration of homeostasis. In case you don't remember, homeostasis is your stable internal environment. It's the environment your body wants to be in all the time, okay? When you disrupt homeostasis, as you do through exercise, your body's going to work hard to restore homeostasis, okay? It's rapidly restored after light intensity activity. It just takes longer to restore it after high intensity activity because there was a bigger disruption of homeostasis. Lactic acid accumulation, we could say, greatly disrupts homeostasis, and therefore it takes a longer period of time to restore homeostasis following an activity that leads to a lot of lactic acid accumulation. So to put it simply, your breathing is going to stay elevated even slightly. It might even be imperceptible to you, but it's going to stay elevated for up to a day to 2 days after a very high intensity activity, especially if it's a longer duration. Like if you run a 5K, if you've never run a 5K, you may not know that you can run almost all out in a 5K for almost 20 minutes if you're well trained. And it's very disruptive to your body. So if you race a 5K, your EPOC is going to stay elevated for probably a couple days afterwards. Where if you run a 400, still all out, but it's not sustained as long, so your EPOC will be less than it would be if you ran a 5K all out. All right, I want to wrap it up. Oh, perfect. That was the last slide. Okay, because I like to keep lectures to around 45 to 50 minutes because I know that after that, your attention span, a human's attention span starts to drop off. Mine included, okay? So I hope that gave you a good review of the energy systems, how they contribute to different activities, and how, intensity, duration, recovery are all sort of related to the energy system, and chiefly for this class, how identifying the energy system or energy systems that an athlete primarily uses can help guide your development of a training program. What intensity do you need to use? What duration do you need to use? What recovery period lengths do you need to use, okay? We're going to get more into that as we go. This is sort of a way to introduce the topic. So this week, your tasks are simple. Do the lecture study questions for Chapter 3 and then complete the critical thinking assignment as well. If you have any questions, comments, or concerns, please give me an email. If you want to schedule a Zoom call to discuss anything in person, so to speak, I'll be happy to do that with you as well. Have a good week. Take care.